Welcome back, chat. Yeah, indeed. Special shout out to my Patreon viewers out there. Today, we are going to start in with 6.2. Now, we are going to be talking more about electricity today, and specifically those electric charges in the form of electric current. Now, do you guys remember when we talked about thermal energy stuff and we saw thermal energy, heat, and temperature? And they're all like really closely related ideas, but just slightly different. Y'all remember talking about that? Heat and temperature and thermal energy just being a little bit different, but they're all about the same idea. Welcome to part 2 of that with a different piece, but these words are going to be, I think, a little bit more specific towards this context. So, right off the bat, we're going to sneak in. And I made this comment the other day. This isn't even a main section, and this isn't really the whole truth, but it's a good way to kind of simplify it. What's electricity again? What passes through the wires? It's not just energy. Energy is transferred because something moves through wires. You remember the something. So, give me good words, but you're giving me too much. Electricity is the, whoa, that's an F. It's the flow of something, and I'm pretty sure we had this word for word. Of electrons. That's it. Electricity is just the flow of electrons. Now, that is not entirely true, because they don't really truly flow, but that's okay. We'll worry about that as we get to it. If I said, what's moving through the wires that powers these lights? What is it? Electrons. You would be equally correct in saying electricity, but they're just electrons. Now, as we go through this idea, there are 3 different big words that we're going to see today, just so you guys are aware. We're going to talk about the current, which, when I hear that word, I don't think of electricity automatically. What do you guys think of when you hear current? Water. I think of water. I think of a river. Okay. We're going to talk about voltage, which that one's a little bit harder. Anybody have a thought in your mind other than battery?
Charger.
A charger? Maybe. Okay, voltage is very specific, and there's one more that we're going to talk about. It's called resistance. Voltage, current, and resistance are the 3 sides of the same coin. And I know that coins don't really have 3 sides, but we'll pretend that this one does. So, right off the bat, we're going to sneak in and just start defining these, because they're all related and they interact together. But we're going to define for ourselves electric current. And this is redundant, so my bad on that. Electric current. Okay, this is super annoying, and I totally get it. We are going to use the letter I for current. This is the label that we'll have for current. Just like velocity was a V and acceleration was A, I is current. All right. Now, right off the bat, if I said, what is the current in a river? Do you understand a high or a strong current and a weak current, I think. What's the difference in them? I love that. What was yours? Love that, because it's the same statement, just worded differently. If I have a river and just some amount of water, let's say, don't care how much water it is, Ililuk River over there. You guys have all seen it. It doesn't run very fast. Let's say that I'm standing in that river. Is it going to knock me down? No, probably not. There's some amount of water moving through it, right? That's the current. If I took the river over there and instead of being 25 feet wide, I made it 4 feet wide, but I had the same amount of water passing through it, would the current change?
Yes.
How? It would go faster, right? Or stronger, because we have the exact same amount of water flowing through, but a smaller space to get through, right? So that's what's going to change. As we're looking at it, if you can think about it with a river like that, it's nice and easy to think about it as electricity. So looking at this, we're going to say that this is the net movement of electric charges. Electric charges. Okay, the net movement of electric charges, and I'm going to say in one direction, because it'd be wonky if your river went back and forth. That shouldn't happen. The net flow of charge in one direction, or the net movement. Okay. Now, we have this idea of current. The river analogy is perfect for it. We're going to go back and forth with this idea of water today. Some of these are strange, and there's a bunch of different analogies that we could draw from, but I think this one makes the most sense. So we have I representing the current. Anybody ever seen a circuit breaker in your house? Okay, for those of you that maybe don't know, the reason I'm talking about those circuit breakers is because when you go home and if you happen to remember and look at your breaker box in your house somewhere, you're going to see those numbers with an A on it. We measure current in what is known as amperes. Now, there's a shorthand for amperes that shows up much more commonly. Amps. Okay, so if I said that river over there has 50 gallons per minute flowing through it, that's the current that we're looking at. Alternatively, if we move from the river to an electrical wire with current flowing through it, instead of saying 50 gallons per minute, we would say 50 amperes. Now, when we look at these, this ampere, it has a specific value. We don't get crazy with stuff. What do you think the shorthand for amperes is? So amp is just an accepted like speaking shorthand. Short speak? I don't know what that would be. Nickname? Is there a word for that? For shortening a word? Like
abbreviations like
sure. Any of those I'll take. Check it out. Don't remember what. Oh yeah. When we talk about amps, you could write 1 amp or 1 ampere. Much more common to just use the letter A. Okay, so when you go home and look at your circuit breakers, you're going to see 15A or 20A written on it. That's just saying how many amperes can those wires handle. Okay, so 1 amp, it turns out, is a definition. And we're not going to go crazy with the units, but I want you to be aware with it. How do we measure charge? Not volts. Like, we use C something. Capital C.
I can't say it.
Coulomb. Okay. We know that, and this gets wonky, we're just going to barely touch on it. Coulombs. Coulombs. What did you say? I wish. No? Okay. You guys wish too, right? Yeah, obviously you do. I don't know. All right. 1 ampere. What's a coulomb, by the way? 1 coulomb. It's an amount of charge. How much charge is it?
10 to the 18th. 6.241 times 10 to the 16th.
So 6.2 times 10 to the 18th, like a crazy big number, right? It's the charge of that many protons. What's the charge of a single proton? 1, positive 1. What's the charge of a single electron? Negative 1. So when we look at this, we could say that 1 amp is some absurdly large number, just like we did before. Or we could just simply say, hey, it's 1 coulomb of charge per second. So every single second, if you have a 1 amp current, it's like there's 6.2 times 10 to the 18th electrons or protons passing by. It's a huge number. Instead of doing just that many little particles, this much charge, which is a lot, every second. So it's a rate of change. Okay, some of that's ugly. Okay with it, at least for just accepting it. Okay, yeah, there's not a great, unless you want to dig into the nitty-gritty stuff, but we don't have the math ability to do that. Okay, beyond that, a little additional piece of this. If we think about particles and wires, this idea of the flow of electrons is pretty natural because it's like the flow of water in a river. In reality, there's some wonky things that happen. If I'm an electron, and I'm in part of an electric circuit, and I'm part of this current, if I'm an electron and this is the wire, it's pretty common to want to think that if I'm going to power something down there, it's like me as a literal electron walking down here, from there to here. That's a natural way to think about it. What's weird about it is that's not the real way that electricity works. It can, but it's not the way that we go with. Electricity for us does this. So instead of just walking one direction, I go back and forth. Now, I'm not really the only electron that's moving. How many more electrons are there between me and wherever I'm going? Probably like trillions of trillions of trillions and trillions of them. Okay, I'm moving back and forth. If I bump into somebody, is that energy going to transfer?
Yes.
Like we've seen that, like pool balls. It's really me doing this. I'm rocking back and forth, maybe overall working that way. But it's not like I'm really just traveling straight down. I'm wiggling back and forth just like we saw with particle stuff. We'll get to it, we'll see it work, and there's some weird things with current, but we have that happening. Okay, beyond that, typically drift in the same direction. Now, that drifting is what I mean by that wiggling back and forth as we're slowly working our way down there. There are two types of electric current that you might be able to find, AC and DC, maybe a name of a band. Yeah, for real, because I don't know why something about electricity. They have a lightning stripe in their name, don't they?
So many songs with like electricity.
Yeah, thunderstruck, like, yeah, they're clearly based on electricity. Cool. That's all I want to say about current right now. Okay. This next one is always so strange, and I'll try as many ways to approach it as we can. What's the label for current? What letter do we use for current? Not its unit, but its label. I. How do we measure current in? What's the unit? Coulombs per second is fine, but there's a better one. Amps. Okay, amps. Now, if you were to look at any charger of these, my bet is if I look at this closely enough, there's going to be MA written on this guy. In fact, I do see it. The output of this thing is 5V, whatever that means, and 2500 MA. MA. Milliamps is much more common of a measurement. I'll tell you, amperage is the dangerous part of electricity, but they all work together. I could survive 1,000,000 volts.
1,000,000 volts?
1,000,000 volts, which we'll talk about voltage here in a second. I could survive 1,000,000 volts. I can't survive 1 amp. Not a chance.
How much is 1 amp in volts?
So they don't work that way, which is a weird idea. Now, realistically, if you have 1 amp, the voltage is probably fairly high. We'll talk about voltage, but amperage is the more scary part. Okay, current, amps, done. Beyond that, let's talk about voltage. Now, voltage, we're going to define it, and it's more common that instead of voltage, like volts is the really common language that we use because there's 9-volt batteries, right? Like we know that, we've seen that word. More appropriate than voltage is this idea of potential difference. These are the same things. I prefer the word voltage because it's a bit nicer, but you may see voltage, and even in this textbook, just so you know, you do see it. You see voltage presented as a potential difference. Okay. What's current? The flow of what?
The net movement of electric charges.
Of electric charges. And in my head, I think electrons, just so you guys are aware, but the flow of electrons, that's what I think of as current or electricity. Now, for voltage, there's more pieces to electricity than just the electrons that move. And this part's a little bit harder. For this, we're going to think of voltage as the cause of electrons, or electricity, but I'm just going to use electrons, getting pushed through a conductor. Okay. Voltage is what causes the current to flow. In our nice river analogy, what causes the river here to push that way? So gravity is a good part of it, for sure. Where does the water that feeds Ilula come from? From the, not the ocean. It's a snowmelt on the mountains, right? And back to gravity, though, we see that a bunch of water up here, it picks up speed and it gets pushed down, right? Gravity as it comes down, and there it is. For this, as we look at voltage, there's some weird ideas. Right off the bat, one little easy comment to make. What do you think we're going to use for the label of voltage? V. Voltage V is easy enough. It's a capital V, just so we don't get it confused. Measured in, and this is, it seems so dumb when we write it. What do you think we're going to measure voltage in? Volts. Okay, I hate this kind of stick, but what do you think the shorthand for volts is? Nope, it's still capital. Okay, now, for this, we've all seen at least the word voltage somewhere. We have current, which hopefully makes sense if you never thought about it. We have voltage, which is what's actually pushing this stuff through the wires. More commonly, and even your textbooks does this, we have this word potential difference. When we think about potential difference, I'm just going to sneak this in. It is the difference, and this is just an alternative or an additional kind of explanation of voltage because it's a strange one. The difference in energy between 2 points in energy between, weird, between, and I know how to spell, 2 points on A, and I need to pause here for just a second. If I were to test the amount of energy that something has and 2 points of a circuit, we've never used the word circuit. Do you guys have an idea what I mean when I say a circuit? Show me with your hands a simple circuit. Love it. Everybody just did it. Okay, this circuit, they're not connect, right? Now they do. This is a circuit. That's the most basic idea. I'm okay with using that word here. Okay. Doesn't have to be a circle, but that's what everybody did. I'm fine with it. Now, there are some interesting things that wind up happening with this. To make sense of voltage, I'm going to go back to that water analogy, and I just want to think of a situation here. And I think I have both of them covered. Yep, love it. Okay, so check it out. In this situation, we have on the left one, we have a water pump powered by something. Who cares what it's powered by? It lifts water up into this tank, which then fills, and then it pushes down through here, and it turns this water wheel. Everybody good with that? Yeah. Okay, it then drains out of the water wheel, and it gets pumped back in, and just keeps repeating the process. If I looked at just this water right here, just that flow of water right at this point that's hitting this, is this me thinking about the current or the voltage? This is the current. This is the flow of the water in this situation, right? Now, in contrast, if I had less water overall in this entire system, and it only filled up to right here instead, would the water pass through as fast? Would the current be as strong if I had less water in that upper tank? No. What would happen with the current if I filled the water all the way to the brim? It pushes faster. Why would that happen?
More weight.
I'm okay with that. I heard weight, gravity. It's more pressure because there's more weight. It's more potential energy, right? I want to stress potential energy. What did we call that voltage again? It could be a potential difference, right? So potential energy, we can make that connection. More energy here pushes faster here. Same idea with this. In this situation, we think about this distance or the amount of pressure here being our voltage. More pressure, more potential energy, more current flows because higher voltage. It's the voltage it pushes it through. In this situation, it's a little bit different, but electrons move through this wire, right? Now, they move through, they do something. It's the turn the water wheel example, but it's a little bit neater than that. And they light up the light bulb, and then stuff flows back through. If I were to check here and here, is there anything that's making the flow go faster or slower between those 2 points? So if I were to hook up something to measure the voltage, what do you think the difference would be between those 2 points? Nothing. Nothing at all. There is no difference between them. If I did it here and here, now is some of that energy going to get used for something else? Would there be a difference in the amount of energy in the wire before it powers the light bulb and then after? So not as intuitive, but let me check. Is there a difference in how fast the water flows out of this, that, and how fast it drains in? There has to be at least a little bit, right? Because it fills up a piece of the water wheel and then it tips out. There's a difference in how fast the water moves through there. Okay, that is a difference in the pressure or the voltage, just like we have differences here. It's a strange idea. We will play with the simulation on Monday to really kind of try to get our hands a little bit more familiar with it. But it's the pressure, the push of the electrons. That's the best I can do for now. Cool. So when we're looking at these, there's some terrible things that happen, and I despise, like not bad in a bad way necessarily, but some things that really bug me, and they bug everybody, but we're this far committed already just in the world of talking about electricity that it's too late to turn back now. So it kind of sucks. As we look at these, we're going to focus a little bit more on electric circuits. So here we go. We're going to talk about circuits and we're going to define it real quick. And then we're going to take a quick brain break, really quick after we define this. An electric circuit. Okay, you guys all showed me a circle before when I asked what a circuit is. Right now, if this is what I'm looking at, this is my circuit, will this power anything? Just my fingers, forget it on my wrist. Right now it's powering whatever's there, right? Is it now?
No.
Why?
Because it's a short circuit. Broken.
It's broken, right? There's a very clear stop between the flow of energy from this finger to this finger. Now, as we look at this, if we want an electric circuit, we need a closed path, or at least the ability to close it, a closed path which current travels through. Okay, we're going to take a short minute here. Everybody's going to stand up, move around a little bit. With true sincerity, and I'm not going to come and listen, but don't be like rude to each other because it's funny sometimes. Not now, though. Cool. I've said it like 10 times probably today. Without looking, can you tell me or answer the question, what's electricity?
Electricity
It's the flow of electrons. We know today with modern technology that it's literally the electrons flowing through a wire. Okay, electrons are bigger or smaller than their positive counterparts called protons?
Same.
Smaller by a lot, like almost zero size compared to a proton, which is really small already. Okay, we all know that electricity is the flow of electrons. Okay. We only know that because of modern technology, and by modern I mean like 1900s-ish, like early 1900s is when technology got developed, but people knew about electricity before that. Edison made the light bulb, or Tesla, or whoever actually wound up making all that stuff in like the 1870s and 1880s. Okay, as we look at this, it means they didn't quite have an idea of this. Drives me crazy. So we're going to look as a follow-up at current and flow of electrons. Now, we know very specifically that electricity and current, which carries electricity, is the flow of electrons. We know that today as truth. They did not know that 100 years ago as truth. And I can't say for any good reason other than because it's the way that they decided to write it when they first started doing this, and it stuck. This drives me crazy. Conventional current. Which, if I say by convention, do you guys know what I'm referring to? Convention. So, like, I'll just totally not science related. If you greet somebody, you ever say, how's it going?
Yeah.
Are you legitimately asking them to stop and explain how they're feeling about things and why at that point in time?
No.
No. By convention, how do you answer that question? How's it going? Good, right? Like that's, I'm really not good, I'm doing well because I haven't done a whole lot of good today. Haven't done a whole lot of bad either, but no, you guys maybe the grammar joke doesn't work, okay. All right, by convention, you all just answer good, right?
Yeah.
Or if somebody says, what's up? Even if you got a lot going on, well, not much. Right? Like that's just by convention, that's the way that you answer that question. That's all that we mean is by convention. Now, super annoying in the context here. Conventional current, by convention, it's the direction and rate that positive charges. Conventional current is the direction and speed, or rate, whichever one you would rather deal with. I think rate is a better word, but speed feels more natural, of positive charges. Okay. Specifically positive charges moving, or flowing, if you will. By convention, and you'll see this if you ever do anything with electricity, even today, you'll still see it. When we look at a simulation, you'll see it. Actual current is the flow of what? So current could be water. The flow of electricity, called current, so an electrical current is the flow of what's actually moving through the wire. It's electrons. That's what's actually moving through the wire. We've hit it like 100 times now. Electrons move. However, in the 1850s when this was being worked out, they thought that what moved? Not the negative charges,
Positive.
the positive charges. So even today when you're looking at stuff, you'll see things that show you which way the protons or the positive charges move, with the understanding that that's not really what happens. It's just stuck, and I hate it, but we have to deal with it. Okay, now, real current direction, if we write it down backward, and let's say I have a current leaving me, so I'm going to be a battery. If I say conventional current goes that way, so to your right, which way are the electrons actually moving? To the left. Okay, it's super strange. Protons moving isn't what happens. It's the electrons moving. It's the exact opposite. Now, beyond that, if you have energy and it wants to balance, does stuff go from, oh, and this is weird, one of the weird situations that happens. Normally energy moves from high to low or low to high?
High to low.
High to low, right? That's how things typically move. As we look at this with voltage, because it's a little bit more complex, last statement here, and then we'll get to draw some things here. Electrons flow from high voltage. Am I backward? No. Okay, so before we commit, electrons flow, I have to just commit to it. Low to high. Low voltage to high voltage. Only for voltage. Notice we didn't say energy, which is where this idea gets weird. Low to high. Because if we think about it backward, which is the way that they set it up, if you have a lot of protons over here and not many here, you're going to balance out, right? Like more protons are going to flow down. Sorry?
Water does that too, right?
Water will do that too, but remember, because the way that we define this convention with the positive charges moving, everything flips. And it's weird and it's strange, but we have to deal with it. So let's draw our first little circuit. And just a heads up, you're not going to get any homework this weekend, so sorry. Okay, quick example. I know, right? Okay. So here we go. We're going to draw a battery. And how many volts do we want this battery to be? 127, deal. I've never seen a 127 volt battery, but here it is. Okay, now on this battery, we're going to have two things happen. We're going to say here's the negative end of the battery. And then on here, what are we going to power with this?
Motor.
A motor. Okay, so I should have just committed to it. I'm going to draw a light bulb because that's easier than a motor. Okay, so there's a light bulb that gets powered. Now, hypothetically, if we have a negative and a positive side of a battery, which we of course do, every battery has a positive side and a negative side. Couple questions. I want to know which way does electricity flow? Is it electrons moving and leaving the negative side, or is it protons moving from the positive side?
Leaving the negative side.
They leave the negative and they flow to positive. Okay, so I know that electricity goes through this way. Now, this is the true picture. Conventional current's the exact opposite. They think it's a flow of protons. It's not. Okay, now going through this, if I looked at this and think of this as like a water wheel turning, there has to be energy used to turn the wheel to light up the bulb. Everybody okay with that? Think of a water wheel turning and it's turning a wheel as it hits it. Think of electricity doing the same thing. There's not really a wheel that's turning in here because it's not that simple. But imagine there's a wheel turning and the current's just flowing to turn it. Okay, that's the basic idea of our light bulb. If I checked right here and saw that I took a measurement and I checked right here, between these two objects, what do you think the difference would be in voltage? And I know there's like infinitely numbers that you could pick from, but how much voltage was there before we went in? So we had 127 before, and we use all that pressure to move this, right? And then it just changes back to its regular, I would say almost no pressure, because it has to kind of work its way slowly back, or pump a battery in this situation. I bet we're at 0 here. What do you think the voltage between or across that would be then? What's the difference between the voltages there? Why half? If I said right here is 127 volts and right here is 0 volts, what's the difference between them? And we get the same as a battery. Okay, we'll see this as we start playing around with it. If we switched it the other direction and I took, instead of hooking up things from left to right, if I just switched the things I'm using to test this, what do you think would happen with the number? So I could do this looking at be like 127 minus 0 to get my 127. What if I switch the sides? And it would give me 0 minus 127 instead. What would change? It'd be negative, and we'll see this happen. It does, you will get negative voltages. It just means you're going the opposite direction of what's expected. The number's what matters, not the sign. Cool? All right. I think that this is a pretty natural spot to pause. What's a battery? Uh-huh. Ooh, that's a good question. Let's say a dry cell battery, like a regular AA. How does a AA battery work? We're not going to answer it now, but I want you to try to talk it out with your neighbors. Don't have to write anything. No homework over the weekend. How does a AA battery work is a question I want you to discuss.